Charlie asked a really cool question. And the cool question is this. If we have the fundamental theorem of calculus, why do we bother with estimation techniques? And that's a fabulous question. Think about this. If I want to know the value of the integral from 0 to 1 of the square root of x, which makes more sense? To take the time and effort to estimate this with 10 trapezoids, or to evaluate with an antiderivative? You're probably already doing it in your heads. And we're done. Ta-da. Why bother? And from the perspective of the 18th century, well, 17th and 18th century, Isaac Newton discovers the fundamental theorem of calculus, Leibniz also. And so now the perspective of 17th and 18th century mathematicians is, let's go find antiderivatives. Because if I can find an antiderivative, I can do areas. Quickly, we discovered that there are some functions that do not have elementary antiderivatives. Here's one. If I wish to evaluate this integral right here, I need some function whose derivative is sine of x squared, and it can be proved that there is no such function expressible in closed form. So now what? Well, that really leaves us with two possible approaches. One is I can estimate the value of the integral using the techniques that you know, left, right, point, trapezoidal. Or the other possible approach is that I could estimate the function in some way by expressing it approximately as maybe a polynomial or some other kind of function. That technique, which you're going to learn a little bit of in Calc 2, is a technique that complements what we have learned so far. And those two techniques are basically the foundation of modern day analysis. All of the cool text stuff that you guys deal with, for example, voice recognition. When you say, Siri, what temperature is it outside? And she says, I cannot answer that question. Well, what's going on there is that your voice is being sampled by a microphone, and those samples are being represented approximately by a sum of sines and cosines at different frequencies. We're taking some weird complicated function and we're estimating it in terms of what's called a trigonometric formula. And that's state of the art for the 21st century. So the estimation that you're doing here, although it seems a little bit tedious, it does seem tedious, right? If you can imagine that if you automate it through a computer, it can become very powerful, and it's broadly applicable to a wide class of functions. So the reason why trapezoidal is simply that it's very general, and if I have a computer, I can execute it with a large number of trapezoids and get a very good answer. Does that make sense to everybody? Okay. Our big story for today is integration by substitution, and I have a packet for you. And like last time, the homework problems are indicated in different symbols on the back, so that you will have some problems to do for tonight, tomorrow, and Friday. And then here, and one for Miley. Miley, I have your packet, and we'll have to do it when you come back.
Oh, sorry, Amanda. I'm sorry. Get it back.
There you go.
Before I dive into integration by substitution, are there any burning questions that you have concerning homework or anything else that are bothering you? Uh-huh. Why do we want to know areas under curves? Well, it turns out that areas under curves represent things just like slopes of tangent lines represent things. The slope of a tangent line, dy dx, represents a rate of change, so that depending upon the variables that I'm talking about here, we're looking at a rate of change of this variable with respect to this one. So, for example, if I have velocity here, then dv dt, which is the slope of the tangent line, blah, 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 has a physical meaning. It has the meaning of acceleration. And if I have, I don't know, what could I possibly have here? I might have something like potential energy. And I might have potential energy as a function of position. And so it turns out then that if I find the slope here of my potential energy curve, then that's going to tell me the opposite of the force that the particle experiences at that point. So all manner of rates of change are expressed in terms of this one concept, which is the slope of the tangent line. Well, what the integral does is it reverses that process. So that if I now start with a graph of force, if this is force versus position, what the integral is going to compute for me is the general sum of force times distance, which you know is equal to work. So physicists in the real world think of work as the integral of force times distance, which is going to be the opposite of the change in the potential energy of an object. Or, if I reverse this process, the integral of acceleration is going to give me the change in velocity. Okay? So the general answer to your question is, if I integrate a rate, I get the total change in motion. Most of the physical models that we deal with are expressible in terms of their derivatives rather than in terms of the actual functions themselves. So when weather forecasters make a weather forecast, they don't have equations that sit there and say the weather is going to be this on this day under these circumstances. What they have is the Navier-Stokes equation that says here's what the rate of change of your fluid flow looks like. And now you have to actually solve that. That's actually a good example of a problem where they don't have antiderivatives for it. They solve it numerically using computers. And that solution then predicts how your air mass is going to flow through. When we see those big arrows and the sweeping or whatever, that's the result of the computer model solving a differential equation.
I have a question. It's kind of like off topic, but just like about what you said. So with the weatherman, so like some people have like a TV, like a really big TV, but then some people it's with a green screen. When they're using their hands and it's all in like the right places, how do they see that? Because they're saying
Move the screen off to the side.
Yeah.
Okay, that makes sense. And then my other question, I think you talked about this in physics last year, but I forgot. When you put ice inside water, why does it crack?
So the ice is experiencing thermal expansion or contraction as a result of changing in temperature, and it doesn't all expand evenly. So you ever play Crack the Whip?
I don't think so.
It's this ice skating game where everybody gets in a line, and now you try to stay in a line as everybody kind of goes around in a circle. What happens is it breaks somewhere because not everybody can keep up.
Right.
And it's the same kind of a thing. You have expansion, but it's uneven expansion. The result is there's going to be a crack somewhere. My driveway, 3 years old, just got its first crack yesterday.
Like a big crack?
No, just like beep, like that. And it's because it's thermally expanding and contracting, and it doesn't all happen at the same rate.
Well, once you get a crack, they're going to expand a lot faster.
Yeah. Okay, let's talk substitution. What we're going to do is we're going to try to expand our repertoire of functions that we can find antiderivatives, so that the fundamental theorem can be a more powerful tool for us. I want to consider, all of you can find this antiderivative. In fact, do so at this time. Go. See if you can do it in your head. Got it? Everybody got it? What'd you get? Did you remember the plus C?
Plus C.
Plus C. That's right. That represents the initial condition right there, the effect of the initial condition. Okay. But watch what happens when I change this just a little bit. Huh. It's in a similar form, right? It's something to the fourth power. So I think to myself, well, let's try it. Is this right? How would I know? Take the derivative and find out. Everybody take the derivative of this and tell me what you find. You can probably do that in your head also, right?
Oh, yeah.
Wait, where's the inside? Keep the antiderivative. You have to take the antiderivative inside of the
Thank you.
inside.
Ah, so what happened when you took the derivative of this? What did you find? Yes, it's close, but it's missing the factor of 2 there. Everybody see that?
Oh, yeah.
What I did not account for was exactly as Matt said, what's missing here is the derivative of the inside. If only I had somehow had this integral instead, then I would have had something in this form. It would have been f of x to the 4th power times f prime of x, like that. And then, according to the chain rule, that would be exactly the derivative of 1/5 of f of x to the 5th. Does everybody see what I'm saying? But I didn't have that. I was missing it. What substitution does for us is it handles that case. It allows us to use chain rule. Substitution is the integral version of chain rule. And here's how the process works. Suppose I'm confronted with some integral, and I recognize that it's in a form that is close to what I'm used to. It is like u to the 4th, except it's not exactly u to the 4th. So I'm going to perform a substitution. I'm going to say, let u equal, and now I'm going to identify an inside function that would make sense for u to equal, and that would be 2x minus 1. So that if I let u equal 2x minus 1, now my integral is going to transform, and the main part of the integrand transforms into u to the 4th. And that's a lot easier to deal with. But there's one thing that's important that we haven't considered yet, and that is how the dx transforms. Because the dx represents a small change in x, I cannot just transmute it into a du. I wonder, what is a small change in u equal to? To find that out, I'm going to go back to my u equals, and I'm going to find its differential, which is the derivative times dx. du is equal to, literally, du dx times dx. And now I can see that dx is equal to 1/2 of du, and since dx is equal to 1/2 of du, then gosh darn it, dx is equal to 1/2 of du. And what I have done now is to transform my antiderivative from an antiderivative in terms of the variable x into an antiderivative in terms of the variable u. Having done that, I can integrate this easily. 1/2 is a constant and comes to the outside. And the integral of u to the 4th du is 1/5 u to the 5th plus the obligatory constant c. I can clean it up a little bit, but there's one more thing that has to happen here. U was a variable that I, the problem solver, created in order to make my life easier. But the original integration was in terms of the variable x, and my answer must be in the terms that the problem was originally given in. It must be in terms of x. So I'm going to clean up by back substituting for u. U is 2x minus 1. Gosh darn it, u is 2x minus 1. Well, I say that because the equal sign in math is so powerful. It allows me to replace this with that. And so many students are reluctant to do so. They will stare at something that says u equals 2x minus 1, and you'll say, okay, what can we do? And it just won't occur to them that I can possibly replace one with the other, right? Until you become comfortable with the notion that that equal sign is absolute. You're not going to catch on to the idea that math is really driven by substitution in a lot of ways. Okay, well, I've performed a complex integration. How do I know if it's right? Check it. Check it. Go. And it checks out. As before, the checking process will give you additional insight as to how this substitution works. So you should check all of your answers, not only so that you know that they're right, but also so that you will quickly begin to understand how the substitution process works. Okay? Now, take a look at this fellow right here. Very interesting integral. In some ways, it reminds me of what? When you see this, what's your first thought? Your first thought's probably arcane, right? Because it looks a whole lot like this. And so we wonder, is there maybe a relationship between these two integrals? And we're not exactly sure. Okay? So I see that I have the x right here, and so I wonder, is there anything that I could do with the x? I briefly flirt with the idea of trying to pull it to the outside, but then I realize, no, that's a constant multiple rule, and x is not a constant. So there can't be anything like that. Then I think, well, maybe could I do some algebra? And I realize that this fraction right here, x over 1 plus x squared, is already as simple as it gets. There aren't any common factors that I can cancel or anything like that. So I'm stuck with the algebra first idea doesn't really go anywhere. And that leaves me with my next line of defense, which is substitution. So I think to myself, what could I possibly substitute? And it occurs to me that maybe what I could do is pull off a substitution of the entire denominator. Maybe I could try that. You'll notice that unlike with differentiation, where you have a bunch of rules and you go pop, 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 with anti-differentiation, it's more of an art form. I can try this. Try that. Let's see what happens. So I'm going to pursue this idea of u equals x squared plus 1, and I'm just going to see what happens. If I do, then in the bottom I get u. That's fine. But I'm not done substituting until every single component of my integral has been substituted away. So let's see what we can find. As soon as I have the du, I want to find as soon as I have the u, I want to find its corresponding differential du. And what is that differential? 2x times dx. Dx is not an optional decorator here. It represents the small change in x, and this is saying that a small change in u is going to be the rate of change times a small change in x. Okay. Well, now I look at this, and I see that this fragment is identical to this fragment right here. Everybody see that? Yeah. And so I say to myself, oh snap. And I solve for x dx. X dx is 1/2 du, so gosh darn it, x dx is 1/2 du. Ta-da! And now I have substituted away the entire integral in terms of u. Out comes the constant 1/2. And then I think to myself, what is this integral? The integral of du over u. In other words, what function has a derivative of 1 over u? Natural log, that's right. And specifically, the natural log of the absolute value of u. Let's see. In order to clean it up and finalize my answer, I need to back substitute. And I need to check it. And that's going to give me 1/2 times 1 over 1 plus x squared times the derivative of the inside, which is 2x. And would you look at that? It works. That's pretty cool. A warning about answers involving natural logs. It is very, very common for answers involving natural logs to be changed in some way using log properties. Here are a couple of changes that you might see. First of all, you might see somebody recognizing the fact that 1 plus x squared is never smaller than what value? 1 plus x squared is never smaller than 1, exactly. And therefore, 1 plus x squared is always positive. And if I take the absolute value of a positive value, what do I get? It's itself, right? So you might see it written without the absolute value signs, because 1 plus x squared is always greater than or equal to 0. It's actually always greater than 0. You might even see log properties used, because a a power times a log is the same as the log of a power. And so you might see the answer rewritten like this. When you see that sort of thing, don't freak out. Just think to yourself, did log properties happen here? And just do a quick check to see that your answer and the answer that's given are the same. Does that make sense? Yes, no? So, how does the substitution happen? Let's break this down into two pieces. The first piece that's easiest is the back half, and that's actually executing the substitution given a U. So I want to practice this at this time. Here's an antiderivative. And I'm going to give you the U to use, which is going to be pi x. Go ahead and compute this antiderivative using that given U. Go. So we have one is you can't expose everything. So that happens. Yeah. Changing the substitute. So I have to that. You can get your PX.
Oh, so then you put the cosine and then one over.
So far. What is dx equal to? 1 over pi times du. Exactly. It requires you to do a little bit of reverse thinking, right? I want you to think about it. Yeah, do what you want to do. Here's what you think. Don't try to use your head this time. How do you know?
Because you put it back in.
To actually work it out on paper. Doing it in your head is a skill that you're going to acquire really quickly. So I'm not even doing it in your head. But you want to walk through the process of being able to do it several times.
And do we do derivative or just plugging in like negative sign?
Negative sign.
Right.
You almost have to do
Oh, yeah.
Oh, you got it. Yeah.
Did you check it? Ah.
No. One.
I want to give a big warning here, and this warning has to do with something that's going to happen in the future. And that is that I'm seeing some of you guys doing this as an intermediate step. And the problem with this is that it's what I call a mixed form. It has two different variables going on the inside. And the mixed form is going to be really problematic when we do definite integrals, because my limits of integration have to be in terms of the variable of the integral, in terms of u or in terms of x. And if I've got a mixed form, then that makes no sense. So, no to mixed forms. You should not have any work at all that shows two different variables at the same time in your integral. Instead, what we're going to do is assemble our new integral in pieces. So I think what you were trying to accomplish with the mixed form was to try to get one piece at a time, and that's totally cool, but we're going to do it in this way. We're just going to assemble the integral in parts, like this. I compute my du, and I get dx is equal to 1 over pi du, which allows me now to directly substitute right here. Tommy, you got this far, and what did you do after this?
Well, I took 1 over 5. And then multiplied by dq.
Uh-huh.
You take the 1 over pi outside and then
Yes.
the derivative is sine u, is sine.
What integral property am I using that gets me from here to here? Constant multiple rule, that's exactly right. And now I have the antiderivative of cosine u, and the antiderivative of cosine u is sine u. And finally, to clean it up, I get this. How many of you got this? How many of you checked it by taking a derivative? How many of you should have checked it by taking a derivative? Checking by taking a derivative is not an optional decorator. It's something that you do in order to be a professional mathematician, so that you know that you're right.
Checking in your head, okay?
Checking in your head is okay-ish. But at this stage in the game, I would say checking in on paper is probably better. I understand the allure of wanting to do everything in your head. I get that. I like to do stuff in my head. At the same time, from experience, you want to have a little bit of a paper trail for yourself at this time. Okay, good. Let's see here. Let's do another one.
Oh my god, I don't know what's going on.
Yeah, I like this integral right here.
I know it's gonna be
This integral, interestingly enough, is the one that you would use to compute the average value of x if x is normally distributed in statistics. So let's go ahead and find this antiderivative, and I'm going to give you the u that you want. Go. If you're stuck, compute du. Okay, so the spirit of substitution is to be guided by the du's. Okay, we have those. First,
Yeah. Just pull that. It's not a it's one word. It's negative. It's not negative.
What's
This is negative.
No, because he's dividing.
Breakfast too. It's negative.
No, because you're dividing.
Really? Oh.
Yeah, again, no go do it. Instead, just simply here. I want to start with these fragments. You cannot transmute. So we're not changing it. So where do you see fragments? Where do you also see it? Now I'm like, where do you see fragments here? Take a look. Where do you see X and X? DU is negative X dx, which is pretty darn close. Close. All of the parts of the integral with anybody else that's struggling with this? Yeah. No. There is no variable.
Did you figure it out?
Yes,
So the negative one comes out to that side. You get negative and you plus equals negative to the side. And plus and you get negative
But anyway, you should not have
No, I want to go on.
But see, this is the limitation. It's possible to do that. It is possible to do that if you have that experience. Matthew, I told you. I told you no mixed forms, and what did you do? You wrote a mixed form. It's like you don't listen, except that because they should listen.
No, I do listen.
Of all of the students that I have, you were the least listening of all students.
Talks, but he doesn't listen.
Whatever I say, you are determined to do the opposite, because you are smarter than me.
Use your reverse psychology. Did you mention one last time?
So as soon as you tell me
Yeah, listen. I just think it's almost the opposite of what he's saying.
Alright. Now, our first order of business is to compute du. And when I compute du, which is the derivative of u times dx, what do I get, James? Negative x dx. The dx is not an optional decorator. It represents a small change in x that I multiply by rate of change to get a small change in u. So think of it as rate times time equals distance. Okay? Now I come back to my integral, and I do not write my integral with mixed forms. If you have an integral that has u's and x's in it, you're wrong. This is my sternest look. And you weren't the only one. So I'm going to come back and I'm going to think in terms of substituting, replacing stuff that is equal. What do I see in here? What fragment do I see in here that is obviously equal to something? The negative x squared over 2 is obviously equal to something. What is it? U. Okay. Now, that leaves me with some other fragment. No, it happened again. That bell is set wrong.
Now it's 4 minutes, Riley.
Yeah. Now I'm left with this. And I look over here, and I see, lo and behold, this fragment is equal to that fragment. X dx is equal to negative du. So I can replace the whole fragment, all of it, with negative du. And this gives me now an integral that I can easily do, which gives me negative e to the negative x squared over 2 plus 6. How do I check it? Take a derivative. So I take the derivative. And I get times the derivative of the inside. The negatives cancel. And I get exactly as advertised. It's a beauteous thing. I'll see you tomorrow.